I'm very happy to introduce Joonhyun from, he's visiting Princeton, but he's affiliated also with the KIAS. KIAS is a Korean Institute for Advanced Study. So he will tell us about the local well-posedness and smoothing of MMT kinetic wave equation. So we're very looking forward to it.
Yeah. Thank you very much. Thank you very much for kind invitation, introduction. And this is my first time visiting USC, and it's really, really nice. And I'm very happy to see all of you. It's my great pleasure. And today I will talk about some local well-posedness and smoothing effect of the kinetic wave equation from MMT, which I'm going to explain. And this is joint work based on the joint work with Pierre Germain in Imperial College and Zhiyuan Zhang in Northeastern. Okay, so maybe I should first start with what do I mean by the MMT equation, but actually we'll never see this equation again in the rest of the slides. So the equation is some sort of dispersive, nonlinear dispersive equation, which has something like a Schrödinger, like some Laplacian-like operator, plus some nonlinearity displays here and there. Yeah, because I'm not gonna explain anything about this anymore in the later slide. I'm gonna be very sketchy about it. But the idea is that this is some dispersive equation where the domain is either a whole real line or some large torus. And here the D is just like an operator for the half of the Laplace operator, like square root of Laplacian. And the power of the linear part is somewhere between 0 and 1. And beta, which represent the a strength of the nonlinearity, is some real number. At this point, I'm not going to care much about it. All the because everything will going to be pretty much formal until we get to the solution and try to analyze it. And this model is well, of course, first when you first see this equation, then probably the first question you might ask is why do you care about this kind of equation? Of course, because it looks complicated. There's no clear a physical interpretation for each term. But this equation is introduced by Majda, Mclaughlin, Tabak as a toy model to understand wave turbulence, which I will briefly explain later. Well, why is this a toy model? Although this looks pretty complicated, this is toy model because this is one-dimensional. Because it's one-dimensional, then it's much easier to analyze the phenomena, what is happening there. Yet still, it presents some rich phenomena. Okay, then what is the wave turbulence? Well, here the expert in the field is in this room. So please correct me if I get it wrong. So, for example, if you have some dispersive equation, then there are lots of questions you might ask. But in terms of some statistical questions regarding to the one dispersive equation, then there might be the question what would be there might be two questions that we may ask. Of course, there might be more. The first thing is how the solution will behave generically in the long run. A generic long-term behavior of a solution is the one question that one might ask. And another question comes from the our observation, either a physical observation or some numerical experiment that which is pretty similar to what you see in hydrodynamic turbulence, that if you excite your system in the low modes and you put some sort of a dissipating mechanism on the very high mode, for example, in Navier-Stokes equation, think about the hydrodynamic turbulence, then you excite the whole system by some large scale force, while the viscosity plays a role that in the small scale is gonna be dissipated away. Then what you see is that, of course, in the a very small scale, in the large scale, which is dominated by the large scale forcing that you put in, or the small scale, which is dominated by the damping or dissipating mechanism, they will gonna have some different behavior. But in between, people see some sort of power law behavior, although it looks more like a line, but they are the axes are scaled exponentially, so it's actually some power law. You see some power law type behavior, and we would like to understand such a power law spectrum of the energy. in many of the force dissipated system. So can we try to explain it? Is one of the questions you might ask in the statistical study of dispersive system. Okay, so people try to understand this question. And for now, let me just forget about the MMT equation and try to explain things in terms of cubic nonlinear Schrödinger equation, because it's more, it seems more, better. Okay, so we have some cubic nonlinear Schrödinger equation, which we regard as some model for the smaller scale, and then physicists have found that at least there are certain regime that we can deduce some conclusion in terms of some statistics, some statistical sense. So what is the regime? We call it the weakly turbulent regime. Why is it called weakly turbulent? First, the nonlinearity is pretty weak. So in terms of size, this one is much weaker than the dispersive effect that you have. So nonlinearity is pretty weak, and also the system itself is confined in a sufficiently large domain. So we are confined in torus, but size of torus is getting larger and larger and larger. Therefore, we enjoy more and more degree of freedom for the system. And finally, we have some randomness in the initial data, which is initial data is randomly distributed in phase space. So we have initial data in the frequency side. Initial data looks like this, where theta k is a random variable, which is independent and identically distributed. So we have some random data in a sufficiently large system with a sufficiently high degree of freedom, plus pretty weak there's pretty weak nonlinearity. Okay, in that case, well, this is what physicists did. So they did it in a hand wave way. So I'm gonna go hand wavy as well, because there is a rigorous derivation, but we're not gonna talk much about it. So let's say you solve the cubic nonlinear Schrödinger equation, then we formally expand the solution of Schrödinger equation in the frequency side. Okay, then in the weakly turbulent regime, if you scale the time appropriately, then in the frequency side, or when k is in first k is in g over L to the power of d, first because they are on the torus. However, in the limit where the size of torus are getting larger and larger and larger, then roughly speaking, then k is in they are become more and more frequent. Frequency become more and more frequent, and then in the end, we can formally think that the frequencies in the whole are d. Also, the expectation, we put randomness so we can think of some expectation. Expectation of the size of the frequencies for each mode k converges to some continuous function rho t of k. And the thing is that we can actually derive the equation for the rho, which is called the kinetic wave equation, which looks like the following. So we can write down the evolution of the rho in time as some sort of collision operator. And collision operator looks a little bit scary, but it looks like this. So what is this? So first, in the limit regime, there will be many waves which can interact to each other. But in the limit, the waves which preserve the interactions which preserves the frequencies. So you can think of it as it'll be better to start from here. So this is, if you write it down in this way, then this is more or less just like a gain-loss relation. You think of the waves which are interacting, and then you think of the waves which are coming as a resultant. So K and M are the waves incoming, and then you have an interaction, and as a result, you're gonna have L and M, or the other way around. Okay. Then for all those type of interactions, the interactions which preserves first the frequencies. So before and after the interaction, the sum of frequencies are preserved. And another one, preserving the energy. So energy is preserved before and after the interaction. Only those types of interactions are relevant in the evolution of rho. That's the meaning of those two direct deltas. And then, yeah, this is usual gain and loss relation. You have incoming and you have outgoing. So that is the meaning of the collision operator. And of course, yeah, this is everything is hand wavy, and how to derive it is a big question. Of course, yeah, physicists have done lots of heuristic derivation like Pierre, Germain, and Zaharov, but rigorous derivation has been, there has been a recent breakthrough in rigorous justification of this equation, culminating in the recent work by Deng here and also Jaharhani, which is actually long time result, which is the first and the only, by far, only known long time scaling limit result we have in this, like including Boltzmann. And yeah, also there are some partial results like Baumeister, German, Hani, Shakta, or College German. Yeah. So yeah, that's the rigorous justification, and that says that like you fix the time, any time scale, then actually you can control the error up to this time, like a error sufficiently small this time, so that this equation is quite valid. Okay. And yeah, that's what wave kinetic theory tries to do. So we try to coarse grain the dispersive system and try to get some coarse grain dynamics, which is valid in certain regime. And yeah, try to understand the whole system as like with this reduced equation of reduced degree of freedom. And here is one very crude analogy between the Boltzmann equation, which is like a coarse grain dynamics for particles. And this is a very crude analogy. So in Boltzmann equation, it's like the system, the smaller scale system is the particle system. Particles just move, they collide, and then go their own way. And that's the interaction. On the other end, the kinetic wave equation is concerned with the interaction between waves. And second, in Boltzmann case, this is the two particle interaction. On the other end, like here is like a 4, and yeah, more like 3. So we have a quadratic nonlinearity and cubic nonlinearity each. And these are more interesting. So like in terms of degree of freedom, as you have more and more particles, and it's the number of particles for the system, you have more particles, then you have higher degree of freedom, which is quite comparable to the like a large box limit. You have a larger box, you have more frequencies, therefore you have higher degrees of freedom. And the strength of nonlinearity has somewhat analogous to the like a graph. This epsilon is the scale of the ball, scale of each particle. So when epsilon goes to 0, then yeah, of course, the size of epsilon and number of particles should satisfy certain relation, which is called Boltzmann, yeah, relation. Boltzmann grad, yeah, thanks. Yeah, Boltzmann relation. So here, when epsilon goes to 0, then you have particles are smaller, then collision becomes a more and more like a rare event, right? When your particles are big, then it's easier to collide them, but when they are extremely small, then it becomes smaller and smaller. So in that regard, nonlinear interaction becomes it's less dominant event. So this is analogous to the weaker nonlinearity. And this one, and there the nature of interaction satisfies the conservation of linear momentum, which is similar to the conservation of the frequency, and conservation of energy, also similar. So that's crude analogy, and it's pretty. I actually don't fully understand why, but the resultant equation also has some similar properties. So yeah, conservation properties are more or less similar here, but still the resulting kinetic wave equation also has the arrow of time, just like the same as the Boltzmann equation. It has an H theorem. There's some quantity you can define as entropy, which is monotonely increasing time. And also there are some interesting equilibrium, which is called Rayleigh-Jeans equilibria, just like in Maxwellian. But yeah, here one distinguished feature of the kinetic wave equation is that actually there are here. Let me try to not confuse. I'm trying to confuse you by using the terminology equilibria in a little bit confusing way. But I'm gonna explain why I try to distinguish the one equilibrium and the other. Both of them are steady solutions. Okay, but here in kinetic wave equation, there is some different type of equilibrium solution, which is different from Maxwellian. So I'm gonna explain it a little bit further later. Okay, but this is why kinetic waves equation is also quite interesting. One of the reasons why. Yeah. Say. Okay, then we derive some equation. Of course, we had some question before, and the natural thing to do is whether this formulation can give answer to the previous question that we posed. The first question was, what is the long time behavior of the generic solutions of the cubic nonlinear Schrödinger equation? What is expected? Oh yeah, it has been proved. Several results are proved, but not in full extent. The general result that you expect is that, well, the solution will gonna behave more. Yeah, it will gonna develop high scales. So there is a cascade of scales, so spectrum. So the energy will gonna be transferred from smaller scale to higher scale. So that is general expectation. And theory of kinetic wave equation actually says something about this. So this is the result of Escobedo and Velasquez. The solutions of kinetic wave equation shows the transport of energy to higher frequencies. So you have a rho of k of t, then it is they show that rho k t, then it moves over time, that a rho is moving from the smaller k to the larger k. So in that regard, generically, in terms of expectation, recall that a rho was the expectation of uk to the square, then they are moving from the lower frequency centered region to the higher frequency region. Then second one, can we explain the power law behavior? And exactly Kolmogorov-Zaharov solutions are our candidate for those energy cascade phenomena. So those are and yeah, I'm gonna explain what kind of solution they are and why they are different from the usual equilibria, which is closer to Maxwellian in a later slide. Okay, and that's a very hand wavy and a brief explanation, just a introduction of what is kinetic wave equation, what is the wave turbulence theory, and now we will forget about the cubic nonlinear Schrödinger equation again. Because, yeah, I'll just say that you can do the same thing formally for the MMT equation. Yeah, let me just say in that way. And of course, it's not done rigorously. It's all just formal, but we'll just take it for granted. So you do the same thing for kinetic wave equation, for the MMT equation, then you have the same equation, which is a partial T of n is a collision operator of n, which is also cubic. Here you have some other factor coming from the the derivatives d operator applied to the nonlinearities, d to the u there are d psi and then power b over 4 was applied here and there. Then you do it, then you get some other factor because of that. But also the feature that the only interaction which preserves the frequencies and the energy are the only one surviving in the coarse grain dynamics. That property still remains here. So here, the corresponding notion of energy is k to the power of alpha. So in the Schrödinger, it's like a K2 square because the operator was I times I dt equals Laplace. But this is Laplace to the like some power alpha over 2, alpha over 2. So that's why we have the energy alpha. Okay, let me just take this for granted. I'll just like not gonna question on the validity on this. Then can we say something about the well-posedness of solutions, or like what can you say of the solutions of them? Can we even say about the like make sense of the solution? This is in particular matter a little bit because some of the most interesting solution, in particular Kolmogorov-Zhahara spectra, really looks like it's just power law, and you do not expect any kind of integrability for power law type solution, unless like you just like put some weights on like here and there and try to like manipulate. But we try to set up the well-posedness theory for it. And also, let me try to make some further simplifying assumption. We first had like a range of parameters for the like linear part, alpha, but let me just fix alpha equals 1/2. That simplifies algebra a lot. And that's why we are doing that. And second, it's also conventional in the community that like n is even in k. So like n of k equals n of negative k. And in using that, we can actually rewrite the whole system in terms of omega, which is square root of absolute value of k. Because like n k and negative k is just like the same as n of k. Okay, with that assumption, we have some result. So the first result is that we also had a range of beta, which is corresponding to the strength of nonlinearity. Then when beta is negative 1/2 and 0, then this kinetic wave equation for the MMT equation is locally well-posed for certain weighted L infinity space, but actually is ill-posed in certain LP space with P is less than 3. So you can make like you can localize the solution in 3 frequencies, and they like interact in a very bad way so that actually the norm grows indefinitely large. That's the first result. And the second result concerns that beta is between -1 and 1. And again, this is locally well-posed. Near the scaling invariant power data means that n of omega behaves somewhere between behaves something like omega to the negative 2 beta plus 3/2. We are going to explain why this is a scaling invariant power data. And if n has some regularity, so this result is about a little bit smoother solution, then actually we have a local well-posedness. And moreover, we have a certain gain of regularity of the solution. And this is in an a priori estimate, which means that what I proved at the level of construction of solution, actually, I don't know. Probably it's a matter of just like a technique. That I couldn't get for now. Okay, and yeah, please let me know if there's any question or comments. And yeah, let me remark that none of them are actually about there's nothing about the global. Okay, there's no, this is not global result, and global well-posedness is usually, generically, it's not expected. The solution itself just blows up. Even like a power law type solution, depending on what's the value of beta, blow up is a more natural in certain region.
So the domain is all of R, it's not periodic, is it?
In K variable, it is all R. Yeah.
Yes.
And like now we just rewrite everything in terms of omega, so it's from 0 to infinity.
Good.
Yeah. So yeah, you're right. Like we made the box like a larger and larger and larger.
Yeah.
So in the end, we have like a whole R. Yeah.
So this first of all, this n omega is a stationary solution by itself.
By themselves is kind of stationary. It's not exactly stationary. It retains the form with the scalar power depending on t.
Okay.
Yeah, like nt times omega to the negative 2 beta.
And if beta is positive, do you have a result of local opposite in a certain weighted space?
Like this.
Like this one, yeah.
This one, No, actually, this one, the beta, this choice of beta was like really used to like kill off the, yeah.
But do you expect there is some kind of similar results for positive beta?
Actually, not very sure. Probably that's there, but maybe not in this way.
Okay.
Yeah, oh, yeah, but that's a great question. I think like, I have to mention this a little bit further because I'm not gonna say anything about this result anymore.
Okay.
So for this result is basically is just like a ODE in Banach space. You just like measure the collision operator in certain weighted L infinity space,
Yes.
and then like you like try to wrap up with the estimate, which is like a Cauchy.
Okay.
And the thing is that we never use any sort of cancellation in this space.
Okay.
Then therefore the only smallness you can get or only control you can get is use the certain weights. And if beta gets too large, then even with those weights, we cannot control like we cannot make sense or kernel becomes too singular.
Okay.
Yeah. That's why this method does not go beyond like any other range than this. Yeah.
Thank you.
Thank you. But this result, we have to use cancellation. We are using cancellation, and that's why we can go slightly further. But even there, like when beta goes much larger, then it's not really clear how to get there.
But maybe you can use the same cancellation in the first result.
Yeah,
Yeah.
because like here actually I put slightly more Lifshitz here because I just wanted to say that I just want to put like a purely L infinity type, just like some like n omega divided by this guy being L infinity.
Yes.
Because of that, to make sense of the solution in that regime, I wanted to use one cancellation and this is the L infinity level.
Yes.
That's why I put Lifshitz here.
Yes.
Yeah, but other than that, like probably we can start with a much less regular data, but still gain some regularity to propagate this. But I haven't tried that.
Okay.
Yeah, thank you very much.
So how about like H theorem or some
Boltzmann.
like global,
Mhm.
say, property of the collision operator? You also have that here?
Oh, that's a great question. First, for this type of solution, actually like the entropy is initially infinity. So like we can, it's hard to say about the H theorem.
Or you do have a formal.
Formally, we have H theorem. Yeah, formally there is H theorem. But this initial data actually does not allow us to say like a time derivative of infinity becomes something is like a yeah, is less informative in some sense. Yeah. Okay, yeah. Are there any questions? Okay, then let me move on. Let me just go with some more. Yeah, let me just torture you a little bit further. So here, yeah, just for completeness, this is just like the expression of the collision operator in terms of the omega, not in K. You don't have to remember any of this. This is just like another complication. But the thing is that the cancellation cancellation relation or the interactions which preserve the energy or energy or what is it? Energy or frequencies can be rewritten again. But of course, now like this one, which is the square, is the conservation of the frequency because omega square is basically K. But they are plus K or minus K, omega square is. Can be the absolute value of K. And therefore you have to take care of all the signs, epsilon 1, epsilon 2, and epsilon 3. On the other hand, energy is more or less fine. It's just plus omega 1 plus omega 2 minus omega 3 minus omega. But somewhat interestingly, then in principle, there will be 8 choices, right? Plus minus, plus minus, plus minus. However, only 4 of them will survive. The other 4 of them actually correspond to the trivial resonances. That means there are epsilon, epsilon 2, epsilon 3, which is, if you multiply them minus 1, for example, minus 1, minus 1, minus 1, then they exactly correspond to the points where this one is already zero. So you have a detailed balance for those which are like which belong. So therefore they will not gonna contribute to the integral. Therefore, the only one you have is where plus 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 here, plus 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 minus 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 plus plus minus minus plus and so on. That's the one thing. And but still like yeah, you have to be a little bit more careful to justify this rigorously, but yeah, this is done. Yeah, you can do it. And second thing, there is an issue of the scaling. So you can try to put the omega to the lambda omega. So you put some scaling on it. Then you have a factor of lambda 2 beta plus 3 half. Therefore, n omega equals omega to the negative 2 beta plus 3 half is a scaling invariant solution. You start with this form, then it's all gonna remain in this form. However, because of the collision operator, you're gonna have some scalar function, which depends on time. And depending on the sign of it, it may blow up or shrink to the collapse to just nothingness, or it may just like stay there. Yeah, depending on beta. Okay. And I'm gonna say a little bit more about that. And next thing I would like to remark is that when I first introduced the kinetic wave equation, I said that there are two types of different equilibria. The first one is called the Rayleigh-Jeans equilibria, which looks like 1 over C1 omega plus C2, which just looks like some like a reciprocal function. And then in here, for those functions, you have because of the geometry of resonant manifold, the resonant manifold in every point in resonant manifold will satisfy that some of the omegas are 0, or some of the like omega squares are 0, and because of that, this form, if you plug in this form, then in the resonant manifold, this one is 0, and therefore integrand, each point of integrand is 0. So it really has a detailed balance at each point of the resonant manifold. And that's why I call it like equilibrium, because it really like there's no dynamics which can really happen, even at each point. On the other hand, there is another set of equation, actually like only 2 for each beta, which if you plug in this value to your solution, then this is not 0. If you plug in this to here, then this is not 0. So at each point of the resonant manifold, you actually do not have a detailed balance. So at each point, it seems like you can some value can go at some point it can flux outward or flux inward. However, if you integrate everything over the whole manifold, then you have 0. Therefore, this is a steady solution. However, it does not have any detailed balance. So that's why this is sometimes people suspect that this is a model for the cascade of mass or energy, and actually in both like opposite direction. And that's why Kolmogorov-Zaharov spectra is somewhat interesting.
So are these the only ones? So some people have clarified all the steady solutions, region operator.
I think if you actually try. If you try power law type, then I think they are, And this for MMT equation, you can do that. For nonlinear cubic Schrödinger, I'm not very sure. I haven't worked on like it. The geometry is way more complicated. But yeah, power type, then I think this is the case. Well, so in particular, we have 2 different powers in our system: scaling invariance and Kolmogorov-Zaharov or Rayleigh-Jeans. Then in this scaling invariant regime, actually the beta equals -3/2 or -1/4 correspond to the Rayleigh-Jeans spectra. So if you plug in beta equals -3/4, then you get 3/4. Then you got like n omega equals 1. This corresponds to the 1 of the Rayleigh-Jeans spectra. And second, if you plug in beta equals -1/4, then you get n omega equals omega to -1, which also corresponds to Rayleigh-Jeans. and beta equals 1/4 and 3/4 correspond to particularly Kolmogorov-Zaharoff spectra. So that's why I think this result is interesting, because we can say some well-posedness theory under for the perturbation of the Kolmogorov-Zaharoff spectra, which is like yeah, remarkable. And second, I would like to say some properties of solution, which is smoothing, which is quite similar to what is happening in the non-cutoff Boltzmann equation. So in non-cutoff Boltzmann equation, people like Grassmann and Strain found that actually there is a proof that they found this. It was discovered a little bit before. The regular smoothing effect is discovered before and suspected, but what is proved by Grassmann and Strain that they actually gain some regularity. Yeah, here, sorry, this is ours. Yeah, Grassmann and Strain proved that we have certain Sobolev anisotropic Sobolev space with some like which is called hyperbolic distance, relativistic distance of the regularity gain. And similar to that, we have some sort of regularity gain here. So it looks like we gain a little bit of regularity. And what is interesting also is that we have two different scales, two different regularity gain depending on the value of beta, which is somewhat unusual. But yeah, that is the regularity gain that we had. And yeah, and let me go on to some strategy how to get it. Well, actually the math is easy, so there's nothing much to say. You just sit down and try to calculate and you get it. Yeah, there's nothing more than that. So the first thing you do is you analyze the collision operator a little bit further, and that's where the simplicity of the MMT equation comes into play. It's one-dimensional equation. You have seen that in general, the resonant manifold of the kinetic wave equation can be extremely complicated. For example, if it is like a 3D cubic nonlinear Schrödinger equation, then you have a dk1, dk2, dk3. So in principle, it's 9-dimensional, but the resonant manifold will gonna the Dirac delta will gonna reduce you to the dimension 1, 2, 3, 4. So it's 5-dimensional, right? So it's a 5-dimensional space. It's a little bit complicated. It's actually quite complicated. However, in this case, in MMT equation, it's 1D model. So you have 1, 2, 3 dimensional space. However, the resonance will gonna give you -1, -2. So you have 1-dimensional model. So you have just one parameter in the whole equation. So we may seek some good parameterization for it. Unless in principle, we can do 1-dimensional integral. And in fact, it's even done by the physicists, Zaharoff, Zhiyuan, and Pushkarov and Diaz. They already gave pretty good parameterization for it, which I don't have any idea how they came up with this. But what we did is we just tried to write it in a more symmetric way, and then we actually get some then we can get some parameterization, which actually show you two different cancellation structure. The first one obviously coming from the gain-loss relation, but the other one coming from the geometry of the resonant manifold, which gives you another orthogonal, kind of orthogonal cancellation. And using that, we just, after that, it's just energy estimate. Okay, so let me present what is the symmetric parameterization we had. So this can be written in this way. You don't have to know any detail, but the thing is that we have two different cancellation, J and K. You can see that this is the usual gain-loss relation. Therefore, we have -1 to the power of J really comes from usual gain-loss relation. But there's one more K. That's the one which comes from the geometry of resonant manifold. We have seen that there were 4 pieces. There were originally 8 pieces, but 4 of them were gone because they were trivial. But there are 4 they are somehow folded in together in a very like a complicated way, but in the way that you can use the cancellation. And that's why we have a two different cancellation structure here. And maybe I should say that like this is not completely original. The Pushkarev, Zaharov, Pushkarev, Diaz, and Nguyen already came up with the one with using this type of parameterization. What we have done is that actually they can be rearranged into the form that actually we have one more negative one to the power k.
So this big N is a Lipschitz function?
Oh, N is N will gonna be a Lipschitz function, but Lipschitz means that the derivative is, yeah. Scale invariant derivative. Yeah, in this sense, it's Lipschitz. Yeah. Yeah, it's just like because like with this derivative, things are easier to handle because
Order one, right?
yeah, order one. Yeah. Yes, exactly. Okay. And let me remark one more thing is that here we somehow essentially use that this evenness assumption in K because things can be written in terms of omega has been essential. And I don't know whether we can prove the same structure, see the same structure without this assumption. This is really crucial. So I just wanted to mention. Okay. And then how to really get the estimate? First, we get some L infinity or positive estimate, and then we get some Sobolev estimate, which is actually uniform in the integrability exponent. And then we just take the P to infinity, then we're gonna get some Lipschitz estimate. And this is the function space that we are working on, where N is here capital N is, I think I missed to mention what it is. N is the renormalized version of the small n. Yeah, capital N is the renormalized version. Therefore, now I'm thinking of N is just some bounded function. Capital N. Okay, then maybe like you can ask why are you saying that this is difficult? Actually, of course it's not difficult. Yeah, that's why I can speak something about here. But like somehow at the point that we didn't know that this can be solved was that the main difficulty was that the kernel is actually very singular. Why? If we go to the form of the kernel, this is the prefactor that we had before. This is the prefactor that we had in front of the collision operator. Then you see that actually they have a pretty singular factors here. So the range of beta is -1 to 1. When beta is -1, then this is u to -2. And we have learned from our calculus class that integral of u to the -2 du is infinity. You need at least u to the -1 or slightly better. So yeah, so each term in the kernel are actually quite singular. So we are actually in the position that we cannot even make sense of the integral operator itself. And that's why previous approach used the weighted L infinity space. When your function is guaranteed to be very small to the some power near u equals 0, then you have some chance of controlling it. Okay, so on the other end, we can also use the cancellation relation. So to get some smallness factor, okay, we can use the cancellation structure. Then we end up with loss of regularity. Then can we close the estimate, the finite number of derivatives now becomes some issue. Of course, you can try to say that we can work in the analytic category, but if you wanna close a system in finite derivatives, then it becomes an issue. Okay, so let me try to explain a little bit about this. So first, in the representation, let me go back a little bit. Please take a look at here, V1 and V2 are, which are the parameters here, are of order 1, and V3 and V4 are of order U. And moreover, actually, V1 minus V2 is actually of order U square, and this and same for phi3 minus phi4. So when you group the terms with respect to like a corresponding to U1 and U2 and U3 and phi3 and phi4, which will always have the opposite sign from here. Here like we have a I. Then we will always get some sort of like a cancellation of order U square, or depending on what K is, then U. And from there, we get some cancellation. But of course, then the collision of L infinity norm, the collision operator will gonna be controlled by L infinity norm of the derivative of N. And that's why we have to be a little bit more careful in the next derivative. And also you can get the positivity. Yeah. Okay. But what about the what about the control of the derivative? Here we cannot go in the here we cannot go in the ODE way, because like what we see is that the method is essentially PDE type, because you have to use that actually they are the solutions of like integral solutions of the equation, and you just multiply dn to the 2p minus 1, and then you take the like integral with respect to this, and then you get some nice estimate. You cannot show that the LP norm of this one itself is bounded. It's really hard, and I think it's not gonna be true. Okay, so let's try to analyze this and try to control this in just usual LP space. Then what will be the most dangerous thing? Well, the most dangerous term will be that when the derivative operator hits here, this is the form, this is the this is this equation, and when they were, we have used the cancellation between these two terms here to make sense of the integral. That means that we need second, if we use the same method, then we need a second derivative of this to close the estimate, and that is not we want. We want to close it at the some derivative. So in the end, we have to control this type of term. And it turns out that when k equals 3 or 4, then you can just use the integration by parts. Then you you first write down the mean value theorem, and then you're going to have some derivative with respect to, let's say, omega, and then you can actually toss that derivative using the like transform it into derivative with respect to u, and then you can just toss it. That's not very hard. However, the most dangerous term is the when k equals 1 and 2, because they are really corresponding to dn of omega, and then minus dn of omega 1 plus u squared, something like this. And here there's no chance for using any kind of integration by parts, because like but it turns out that if you collect all those kind of terms together, then actually they have good sign, and that's the source of smoothing. And this estimate can be made uniform in all the integrability exponent p. Then you just take the p to infinity, and that's how you get the Lipschitz estimate. Okay, then finally we try to construct a solution. The thing is, you can just construct a solution by, first, now we see that this cannot be done in like ODE in Banach specs method. You have to really construct a solution and take the limit. So you first construct the approximate solution. Here, the way is that instead of integrating from 0 to 1, you can just integrate from epsilon to 1, and all the estimate actually remains same. So you use the integrate approximate solution using that, and you just use the compactness to extract the solution. But still, there is a caveat, because if you do that, then you only have a, let's say, uniform convergence of the n itself, but we have no control of the derivative of n, and therefore the constructed solution actually we don't know whether it satisfies the smoothing property, because the limit, we do not know the smoothing gain term of the approximation solution converts to smoothing gain of the resulting solution. And that's why I'm not claiming that the constructed solution also has the gain of regularity. Okay, And uniqueness is kind of easy. You just do the same thing for the lower derivative, then you are done. Okay, I think that's all I wanted to say. And thank you very much.
Yeah, so thanks for a very interesting talk. So are there any more questions?
So the little n that you're looking at the evolution of, does that when you said one of the fundamental questions we're looking for was to see if this made any sense in terms of turbulent interactions, right? Turbulent spectra. So little n corresponds to the energy spectrum.
Little n correspond. Yeah.
Okay.
Yeah.
And for certain values of beta, the solution that the initial condition that you were looking for, n of omega is actually increasing with omega, right?
Yeah, for certain beta, it will gonna increase. Yeah, but at least for beta equals to 1/4 and 3/4, they're gonna correspond to the decreasing spectrum. Yeah,
that's the Zakharov.
Yeah, they are the Kolmogorov-Zakharov.
Kolmogorov-Zakharov. Okay.
Yeah. For them, it will look like that. Yeah.
And when it is increasing, is there any other physical phenomenon that is being described in that?
Oh, that's a great question. People have, but I think for negative beta, I'm not very sure. Like, which model can
I think you said that corresponds to the Rayleigh gene spectra.
Rayleigh gene spectra exists for every beta. I don't know. Yeah, it's independent of beta. It's just really about like a gain oscillation there, and yeah, they are always like a 1/omega or like a 1. Yeah. So beta has to do with the Kolmogorov-Zakharov spectra.
So you're basically using some kind of energy estimate, estimating this L2P thing. So if you, I was just thinking, imagine you do a naive expansion, keep iterating this, then you will see like each term is still well defined kind of, but then you are losing derivatives. So what do you expect? Because I'm thinking in terms of derivation. So let's say if you try to derive this from the MMT, you're basically trying to match these expansions term by term. And in that case, you kind of need to prove the convergence of this kind of term by term expansion. And this seems to be requiring you have analytic data, maybe.
Oh, like to justify. Maybe we might need some higher regularity data.
Okay. Okay.
Like if we not try to stop at somewhere, then you need you need infinitely many derivatives for.
I see. Okay, good. Thank you.
That's a great question.
So do you expect any specific regime that you may expect a little bit longer time?
Oh, that's a great question. Actually, the next one I wanted to look at was we try to linearize operator and calculate the spectrum, but it was quite it's quite messy. So I think that's definitely worth trying and see what's going on. So the thing is that linear operator will gonna have anyway same singularity structure. Here this is the operator. Then the issue was the singularity here. Whether this is linear or not actually doesn't help. Linear or non-linear actually doesn't help us at all. So in the end, even to make sense of integral, then we have to play around with those kind of cancellation and so on. But then do you have some additional space to play around with some spectral theory? That was something I would be very interested to see. And I think that's a great question. I looked at it, and I think it's very nice. And also, maybe I didn't explain it here, but probably there are some regime actually, which might be interesting. So if you look at the all those kind of this kind of power spectra, those kind of scaling invariant spectra, and this is the value of beta. And see, if you're plugging in this to here, then if this equals 1, then what you have, according to Mathematica, is the following picture. So -3/4, -1/4, 1/4, and 3/4. And you can see that all they correspond to regularization and they correspond to the Kolmogorov-Zaharov, and they are steady solution, and that's why if you're plugging in this to here, then they are 0. C of the collision operator operated to here is 0, and therefore they were gonna not change. They're not gonna change. That's why they are steady solution. However, in this regime and this regime, the value is negative. Therefore, in this regime, what you expect is that you start from some data, even though it is a power law data, it just collapses itself and going to 0. And in this regime, a blow up is a generic behavior. Even for power law data, this blow up is the data that you should expect, the behavior. Yeah. So yeah, I think that is a very interesting question. If we can go, yeah. So in particular, stability of those 4 points. The 4 spectra is actually a very interesting problem.
Thank you. Are there any questions? Okay, so thanks. Let's thank you again.